Well, here is the exam review for exam number 2. The chapters are DC circuits, magnetism, and AC circuits. Well, not everything is given in the widescreen part, so you'll have to listen to the audio very carefully to get all the questions, or rather all the topics. So number 1, we have to be sure about the units. There are lots of quantities and their units. For example, potential. Potential is measured in volts, but potential is defined as the work done to take a 1 coulomb from one point to the other. So it's actually work done over charge. Potential is work by charge. And work is force multiplied by displacement. Force multiplied by displacement. We can further break that down to where force is mass times acceleration. And again, acceleration is measured in meter per second squared. Mass is measured in kilograms. So finally we get work is equal to, when you plug it in, mass times acceleration times displacement, because force is mass times acceleration. So plug that in there. So you get mass times acceleration times displacement. Mass is measured in kilograms. Acceleration is in meter per second squared. And displacement is in meters. So when you put all those together, you get kilogram meter squared per second squared for work. And then potential is work divided by charge. So we got to divide that unit by the unit of charge, which is a coulomb. And so finally, potential is measured in kilogram meter squared per coulomb second squared. So that's how we measure the unit of potential. Next, we'll look at the unit of capacitance. Capacitance is defined as charge divided by voltage. So the unit of capacitance is farad, which is coulomb over volt. Now that we find the unit of volt, we already found it. We can just substitute it rather and get the unit for farad broken down. So let me just go down to, we've already defined and found that volt is measured in coulomb meter squared, kilogram meter squared by coulomb second squared. So all we got to do now is just coulomb divided by that whole thing, which makes this coulomb square, right? Because this coulomb comes all the way to the top. And so it's coulomb squared second squared by kilogram meter squared. Remember that all this has gone to the numerator. So that's how we find the unit of capacitance. And then we have resistance, let's find the unit of resistance first, and then we'll find the unit of resistivity. Resistance is volt per ampere, all right, by Ohm's law. And current is actually rate of flow of charge. That means current is charge flowing divided by time. So there you see the unit is coulomb per second for current. And then we've already got the unit of voltage, so that's the whole thing. And then divided by coulomb per second, right? Coulomb per second, because that's the unit of I. Okay, so this whole thing is the unit of voltage. And then you have coulomb per second, which when you rearrange, you're going to get kilogram meter squared by coulomb square second. Now resistivity. Resistivity, the symbol is rho and comes from the formula R is equal to rho L by A. When you rearrange that, you get rho to be RA by the length. And we already got the unit of resistance. And then area is in meter squared, length is in meter. So which means now you get kilogram meter cube by coulomb squared second. So there is no way of memorizing all those. They all come from their units and how you break down those units. All right. And here we have three equations or three formulas for resistance. Resistance is voltage by current. Resistance is also resistivity times the length divided by the area. And resistance changes with temperature according to this formula R0 1 plus alpha delta T. So these are three important formulas dealing with resistances, and I'm trying to give an example quickly for each one of them. So the first one comes from Ohm's law. Let's say that the voltage is given. The voltage is 5 volt and the current is 2 ampere, and therefore the resistance of the conductor must be 5 by 2, which is 2.5 ohms. Straightforward. Now for the second one, the radius is given as 1 centimeters, which is 0.01 meter, from which you find the area of cross section as pi r squared. Okay, you have to find the area of cross section because the cross section is circular, and then that's the value of resistivity given. And so we can calculate the value of resistance plugging in those numbers. Resistivity is given, and then I've assumed that the length is 50 meters. So if the length is 50 meters, like I'm making up the values as we go, okay, just to give an example. Pi times r squared. Remember that radius has got to be in meters. And then when you calculate that, you get 0.0022 ohms. Obviously, the resistance is small because the conductor is thick. So thick conductors have smaller resistance, while thin conductors have a bigger resistance. Now for the third one, let's assume that the resistance is 10 ohms at 20 degrees Celsius, and we have to find the resistance at 100 degrees Celsius. Alpha is the temperature coefficient of resistance that will be given, and then you plug it into this formula. So 10 times 1 plus the value of alpha multiplied by the change in temperature. So the change in temperature here is 80 degrees Celsius, and so we get 10.16 ohms. So you see that it's only changed slightly because alpha is really small. So at 20 degrees Celsius it was 10 ohms, but at 100 degrees Celsius it's only just a little bit bigger, 10.16 ohms. In the next question, let's talk about power. Now power is given by three formulas, but basically power is the product of voltage and current. Power can also be the square of the voltage divided by resistance, or it can be the square of the current multiplied by the resistance. So let's assume there is a 60 watt light bulb which uses 120 volt, and we're trying to use this bulb at 240 volt. Now before we start this problem, let me tell you that this bulb is not going to work at 240 volt, because as soon as you connect it to the 240 volt, it'll just blow out. But conceptually, let's imagine that it works, and then what power would it use? So if it did work, we have to calculate the power, for which you have to remember that we have to use this formula now. How do we know? Because we know that the resistance of the light bulb is a constant. Whether you give it 120 volt or 240 volt, the resistance of the light bulb depends on the physical structure of the filament, and so the resistance is constant. So you always have to pick up a formula that involves a constant in that particular situation. So here resistance is a constant and voltage changes. So those are the two quantities. One must be a constant, the other must change. So first we will find the resistance of the light bulb using the formula. Rearranging it, we will plug in 120 first because that's when it produces 60 watts. And that gives the resistance as 240 ohms. Next, we will use the same formula to find the power at 240 volt. So now it's 240 squared by 240, which gives 240 watts. So what's interesting is the 60 watt light bulb now produces 240 watts. That is, if it had worked. It will not, okay? Remember. So if we had done this backwards, like if this was originally supposed to work at 240 and it produced 60 watts, then at 120, which is half of the voltage, the power would be 15 watts. The idea is because there is the square of the voltage. If the voltage doubles, the power quadruples. If the voltage becomes half, then the power becomes 1/4. Basic idea. So that's how you calculate the power in such. Next is the charging of a capacitor through a resistance. So when a capacitor is charged through a resistance, the charge increases on it exponentially. And if the resistance is really high, then it even takes longer time to get charged. So the basic formula for charging is Q is equal to Qm 1 minus e raised to minus t by CR, where C times R is the time constant, okay? So, and Qm is the maximum charge on the capacitor. So let's say C is 5 microfarad, the resistance is 6 mega ohm, and then the time constant is the product of C and R. Remember, mega is 6 times 10 to the 6, so we get the time constant, in this case to be really big, it's 30 seconds, because the value of the resistance is in mega ohms, okay? So 30 seconds, and really time constant is the time taken for the charge to build up to 63.2% of the maximum charge. That is the definition of time constant, and you need to know that. And then, so let's find the charge on this capacitor after 10 seconds. Now, in order to do that, we have to use this formula, but first we have to find the maximum charge on the capacitor. And the maximum charge on the capacitor is just the product of the capacitance and the voltage. Capacitance is 5 times 10 to the negative 6. And let's assume that it's charged through 10 volts. So I'm making up the values as we go. So if the battery charging it is 10 volt, then we know the maximum charge is going to be 5 times 10 to the negative 5 coulombs. And then we can use this formula to find the charge on it after 10 seconds. So we're trying to find Q. We already got Qm. Qm is 5 times 10 to the negative 5. So 1 minus e raised to negative 10 by 30. So negative 10 by 30 is negative 1 by 3, which is negative 0.333 repeating. Okay, so 1 minus that, and when you put it into the calculator, you're going to get 1.417 times 10 to the negative 5 coulombs. That's the charge on the capacitor after 10. This is the conversion of a galvanometer into an ammeter and into a voltmeter. To convert a galvanometer into an ammeter, we got to connect a real small resistance in parallel. Okay, so we can find the value of that resistance by using the idea from the circuit. So here is the galvanometer with the resistance. The resistance of the galvanometer is shown here. We'll call that as R sub G. and the maximum current that can flow through the galvanometer is Ig, which is usually really small because the galvanometer is a very sensitive device, right? So, and if you want to measure a bigger current, I, then you need to provide a safe path for that current through this resistance. So that's what happens. So we limit the current through the galvanometer by taking a smaller and smaller value for the resistance. So from that total current, we're going to have I minus Ig flow through the small resistance while Ig flows through the galvanometer. Now the idea is between these 2 points, between this point and this point, the voltage can be calculated either by multiplying Ig with Rg or I minus Ig with R, because we know that the voltage in a parallel circuit will be the same. So we will set those two equal to each other. Ig times Rg must be equal to I minus Ig times R, from which we can calculate the value of the resistance. So here again I'm assuming that Ig is 1 milliampere, so that's why we have 0.001 ampere. That's 1 milliampere. I've assumed the galvanometer to have a resistance of 25 ohms and that we have to measure a current of up to 1 ampere. So knowing all that, the value of the resistance can be easily calculated. Okay, so there. Now I'm writing down the values that I assumed in my head. Okay. So the resistance comes out to be 0.025 ohms. All right, now to change a galvanometer into a voltmeter, we have to connect a real high resistance in series with it. So here is the galvanometer again with its resistance, and that is the high resistance connected in series. So R sub S is the resistance. So here the idea is, if this galvanometer is now used as a voltmeter to measure up to V volts, then we know that the voltage is the current Ig multiplied by the total resistance, which is Rg plus Rs. So that's the idea there. So the voltage is the product of current and total resistance. Okay, because they are in series. And then we can from that calculate the value of the resistance to be included in series. And so if you want to measure up to 1 volt, again it's the same galvanometer as before, so Ig and Rg are the same. And then we can find out Rs. So that comes out to be 975 ohms. So you see that's a real big resistance to be connected in series to convert it into a voltmeter, as opposed to a small resistance connected in parallel to change it into an ammeter. The force on a moving charge when it moves through a magnetic field. So whenever a charged particle moves through a magnetic field, a force acts on it. All right, so that the direction of the force is given by the right hand rule, and here let's be very careful. See, the fingers show the magnetic field. Now, one way to remember that is because there are many lines like many fingers, so that's the magnetic field. The thumb gives the direction of motion of a positively charged particle. So the thumb gives the direction of motion of the velocity of a positively charged particle, and with the palm you push, so that gives the direction of the force. I hope that's clear. So the fingers give the direction of the magnetic field, the thumb gives the direction of motion of a positively charged particle, and the palm gives the direction of the force. So that's the right hand rule. And so in this case, the magnitude of the force is given by QVB sine theta. So Q is the charge of the particle, V is the velocity, B is the strength of the magnetic field, and theta, as you're going to see, is the angle between the velocity and the magnetic field. So this is the formula to find the force. All right. So the red arrow shows the charged particle, B is the magnetic field, and you see that the angle is between the velocity and the magnetic field. And this is with respect to a positively charged particle. So assuming that it's a proton, again positive, moving at a certain velocity, which I assume to be 3 times 10 to the 3 meter per second, and at an angle of 60 degrees to the magnetic field, and the magnetic field is 0.1 Tesla, we can find the force that acts on it. We know the charge of a proton is 1.6 times 10 to the negative 19, which is exactly the same as the charge of an electron. So Q, velocity, B, sine 60. And you get the answer for that. Now remember that if the charged particle is moving perpendicular to the magnetic field, then maximum force acts on it because the theta becomes 90 degrees. But if they're both moving parallel, like the magnetic field and the velocity are parallel, then the angle is 0 and sine 0 is 0. That means no force acts on the particle. So if it's moving at 90 degrees, maximum force acts on it. If it's moving parallel, no force acts on the charged particle. So, and also remember that the direction is given by the right hand rule. Fingers give the magnetic field, thumb gives the velocity, and the palm gives the force acting. The magnetic field produced by a straight conductor, so if you have a straight conductor in your hand, and if it's carrying current upwards, then hold it in your right hand with the thumb pointing in the direction of the current, the direction of the closed fingers to the tips gives you the magnetic field. So if the current is flowing up, then the magnetic field is in this direction, while if the current is flowing down, then you see the magnetic field is in the opposite direction. So this is right hand rule number 2. And the magnitude of that field, the magnetic field, is given by the formula that you see right now. B is equal to mu naught I by 2 pi r. Now mu naught is a constant. It's the permeability of free space. Mu naught is 4 pi times 10 to the negative 7. All right, we'll get to that in a minute. So here's the formula. And let's assume that I is 1 ampere. And we're looking for the magnetic field 10 centimeters away. And 10 centimeters is 0.1 meter. So here is a visual. So that's a straight conductor carrying current. We're looking for the magnetic field here. The magnetic field is going to be in concentric circles as given by the right hand rule number 2. And let's wait a minute there. So that means at this point P, if you use the right hand rule, how is the magnetic field? What's the direction of the magnetic field? At the point P, which is on the right side of the conductor, the magnetic field, watch this, the magnetic field is going to be into the screen. But if you are looking at a point on the left side, the magnetic field is going to be out of the plane of the screen. So at this point P, the magnetic field is perpendicular to the screen into it. And if we were looking at this point Q, maybe it would be perpendicular to the screen again, but out of it. All right, and the value of the magnetic field is mu naught times I is 1 ampere, 2 pi times r, which gives you 2 times 10 to the negative 6 Tesla. So both the magnitude and the direction are very important in these cases. I hope you understood. Next, we have the idea of 2 parallel conductors, both carrying currents, And so what's going to happen is one is kept in the magnetic field produced by the other current. So each one. So the left one is kept in the magnetic field produced by the current through the right one, and the right one similarly is kept in the magnetic field produced by the current through the left one. So therefore there will be a force acting on these two conductors, and this force can be calculated by this formula that's going to come up. So here we have the magnetic field at the second conductor, which is r distance away, and then we can find the force on that second conductor using the formula B times I times the length. Okay, now B is already B naught I by 2 pi r, because that's the magnetic field produced there due to I1, and the current flowing through the second one is I2. So we get the formula for force here, and then if we assume that I1 and I2 are 1 and the length of the conductor is 1, and also that the distance is 1 meter, so we make I1, I2, L and R, all of them 1. Then we are left with mu naught by 2 pi, and mu naught is what? 4 pi times 10 to the negative 7, and then divided by 2 pi, you're going to get the 4 pi and the 2 pi cancelled, you will get 2. So finally we end up with 2 times 10 to the negative 7 Newton. This is the idea using which the ampere is defined. So 1 ampere is that current which, when flowing through two straight parallel conductors placed 1 meter apart in free space, creates a force of 2 times 10 to the negative 7 newtons between them per meter. It's an important case of trying to find the magnetic flux through a coil. Now here what's very important is, when you take the angle, you do not take the angle with the coil, not with the plane of the coil. Instead, we take the angle with a perpendicular drawn to the coil. So that's very important. So here's the diagram, and you can clearly see that this coil, that's the plane of the coil, and here is the perpendicular drawn to that coil, and this is the magnetic field. So you see the angle is taken not with the plane of the coil. This is not where we take the angle. We take the angle with the perpendicular drawn to the plane of the coil. So that's very important. And then to find the magnetic flux passing through the coil, we use the formula NBA cosine of that angle. So where N is the number of turns, B is the strength of the magnetic field, A is the area of the coil. So assuming that B is 0.1 Tesla and the area is 0.2 meter squared and theta is 60 degrees, then we can find the flux passing through it. And just put in the numbers, 10 times 0.1 times 0.2 times cosine of 60. That will give the total magnetic flux passing through the coil. Magnetic flux is measured in Tesla meter squared, okay? But now imagine that the plane of the coil was parallel to the magnetic field. So the plane of the coil was parallel to the magnetic field. So what happens now? If the plane of the coil is parallel to the magnetic field, then the perpendicular is at 90 degrees. So theta becomes 90 degrees. Cosine 90 is 0. So no flux passes through it. But if the plane of the coil was perpendicular to the magnetic field, so that's a magnetic field. If the plane of the coil is perpendicular to the magnetic field, now when you draw the perpendicular, it's going to make an angle of 0 degrees with the magnetic field. And cosine 0 is 1, which means maximum magnetic flux passes through it. So just remember, in the case of a generator, what we have is a coil rotating in a magnetic field. Now, as we saw before, when that happens, the magnetic flux associated with the coil continuously changes. That induces an EMF. That induced EMF is given by Em cosine omega t, where Em is the maximum voltage, and that maximum voltage is NBA omega. N is the number of turns, we know. B is the magnetic field strength in Tesla. A is the area of the coil, which may be pi r squared, remember that, in meter squared. And omega is the angular speed at which you rotate it in radians per second. So that's the idea for a generator. That gives us the voltage that will be produced in a generator. I've not put in numbers there because that's so easy. Whatever is given, make sure they are consistent in units, like B in Tesla, A in meter squared, omega in radians per second, and you're good to go. In a transformer, there are two important formulas to be remembered. Transformers can be step up or step down. Now, in a step-up transformer, the voltage on the secondary is going to be higher. That means the number of turns in the secondary is going to be higher than the number of turns in the primary. And this is the voltage equation. The ratio of the voltages is equal to the ratio of the number of turns. So you have the S and the S, so that's directly proportional. But when we try to find the currents through the primary and the secondary, remember that under ideal conditions, the power in the primary is equal to the power in the secondary. And power is the product of current and voltage. So that's why we get that formula. Now, if you rearrange that formula, the math will show you that Vs by Vp is Ip by Is. So do not make a mistake there. It's a reverse. So if you start with S there, the S is in the denominator. That means for a step-up transformer, the number of turns in the secondary will be higher, which means the voltage in the secondary will be higher, but the current in the secondary will be lower. So those are the formulas for transformers. This is the LCR circuit. We've done this several times. It's a lab as well. You should be able to calculate the inductive reactance X sub L, which is 2 pi times F times L. So, and XC is 1 by 2 pi FC. Of course, F is the applied frequency. L is the inductance value in henries, C is the capacitance value in farads. Now, when you have all three connected, this is the formula for impedance. Z is square root R squared plus XL minus XC whole squared. All of these formulas are on the formula sheet. You just need to know what they stand for and be very careful when you calculate. And the current by Ohm's law is, of course, voltage by resistance. In this case, we have impedance. So voltage by impedance, and that's the current generally. But at resonance, remember that XL and XC become equal to each other, so they cancel out. So the impedance is just the resistance. So that means the current at resonance, which is going to be a maximum, is simply given by the applied voltage by resistance. Okay? So that's what you understand. And what is resonance? Resonance is that frequency at which XL becomes equal to XC. All right? So you put them equal to each other and then put 2 pi FL is equal to 1 by 2 pi FC. Rearrange that. Do the math. You will get the resonant frequency to be 1 by 2 pi square root LC. And you should be able to calculate that. Remember, inductance has to be in henries, not millihenries or microhenries. And capacitance has got to be in farads, not microfarads. So be careful on that. You should be able to do all those calculations. And finally, I just wanted to review combination of resistances. Resistances can be connected either in series or in parallel, or you could also have a mixed connection. So if resistances are in series, to get the total resistance, you just add them. okay, R1 plus R2, or as many. If they are in parallel, then you go 1 by Rp is equal to 1 by R1 plus 1 by R2. Now remember to take the inverse after you do these calculations, because we're not looking for 1 by Rp, we're looking for Rp. And so this is a mixed connection, because you can see these two are in parallel and this is in series. So in order to calculate that, first you'll have to calculate the value of those two because they are in parallel, and I called it Rp, and then Rp plus R3 will give you the total resistance. So here I've given you a lot of questions, in fact almost all of the questions, and hidden in between as I was talking, if you were listening to me, are almost all of the conceptual questions. So I've addressed 25 questions. If you were really listening to me carefully, you would also get the conceptual questions. But if you're only looking at the white screen, going by the formulas and rushing through it, then probably you only get the calculations. So anyways, I hope you take a look at this and prepare for this exam and try to understand these topics without rushing through them. Good luck on the exam.